Good morning. In environmental chemistry, we're going to talk about different components of the Earth system. So I want to take a moment to define them. In the course, we're going to start with the atmosphere. I think it's pretty obvious, but the atmosphere consists of the common air that bathes the globe. It is predominantly comprised of gases, but there can be condensed phase liquid water, like in this photograph with clouds. There can also be particles in the air. Solid or liquid particles suspended in a gas are called aerosol. So we would talk about atmospheric aerosol in this course. I have an arrow here pointing to the hydrosphere. And in this photograph, the hydrosphere is pointing to the ocean, but lakes and streams would also be part of the hydrosphere. Some people would also consider clouds part of the hydrosphere. I have an arrow pointing to the biosphere. The biosphere are plants and trees. And if you've ever smelled a Christmas tree or cleaned with pine salt, you've smelled organic compounds that come from trees. And this is an emission of organic gases from the biosphere to the atmosphere. The pedosphere is the very interface between solid Earth, the biosphere, the hydrosphere, the atmosphere. It's where soil formation processes come from, or where they happen. And that's right at the interface. And then when I talk about the upper mantle of Earth's crust, I tend to use the term lithosphere, but the textbook we use in this course uses the term geosphere. And so the pedosphere is just sort of the tippy top of the lithosphere. So now you'll have some understanding for what I mean when I mention these different components of the Earth system. So in environmental chemistry, we are going to concern ourselves primarily with the fate and transport of pollution through the Earth system. Some people think that the word pollution is too pejorative, but I think it's actually too nice of a word to describe poison. So when we want to understand the fate and transport of pollution, we are going to concern ourselves with things like understanding what chemical reactions take place. What is the physical mode of transport of pollution through the various media, through the various spheres of the Earth system? How is the chemistry and how are chemicals different in the air, water, or soil, and as they transfer or partition between all of those phases? And when we concern ourselves with environmental chemistry, what the impetus normally is trying to understand, because we are concerned about the impact of that pollution in the food that we eat or in the air that we breathe or in the water that we drink. And your textbook defines impact as the product of population, affluence, and technology. And this equation seems a little cynical to me, but let's go ahead and explore it. So in a modern context, you could imagine, for example, if we were to map out where fracking wells are in the Marcellus Shale region. So if we were to look at the eastern United States, we would find that the permitted locations for fracking wells would be in sparsely populated areas. They would not necessarily be in downtown Pittsburgh, for example. And the reason why is sparsely populated areas have a small population. And so that product that defines impact is lower. The more affluent a community is, this formula would give it a higher impact. And I want you to think long and hard about that and whether or not you agree. We're going to talk about that more in class. And then finally, technology, and that's also something that we'll talk about later in the course. And one thing that's really important to understand is risk is a complicated function. And in two broad categories, it depends on exposure and hazard. So if you have two different chemicals, one is more poisonous than the other, the risk of that chemical might be higher because the hazard then is higher. But also exposure is another equally important part of a risk determination. So if there's poison in the air and you breathe in that poison all the time and you're chronically exposed to it, your risk might actually be higher, even if on a smaller basis it has less of a hazard. It's less acutely poisonous. So that's something to keep in mind throughout the course when we want to understand the impact and risk associated with different types of environmental pollution. This is what we're going to look at. I took an environmental engineering class as an undergraduate, and my professor had this saying, the solution to pollution is dilution. And at the time, when I was a young person, I was sort of outraged. But in some ways, he was absolutely right. If we think about any type of environmental pollution, it's the concentration of it, concentrating it in small locations, that typically is what causes problems. So, for example, if we think about nuclear waste, all of the nuclear material used in bombs, used in nuclear reactors came from somewhere. Typically, this was sprinkled out throughout the Earth system, but then humans came and they either produced synthetic chemicals or they mined it and then they put highly radioactive material close together. And now we have a pollution problem, right? When we talk about nuclear waste, there's lots and lots of examples. But that's why when you have lots of pollution close to each other, like in Yucca Mountain, it becomes a problem. But before that, when nuclear compounds were more sparsely populated around the Earth, it wasn't a problem necessarily. And so that's something else to keep in the back of your mind. The solution to pollution is dilution. So something that's really intrigued me for such a long time is this concept of the precautionary principle. And in the United States specifically, the burden of proof to introduce a new product or a new process falls on the manufacturer to demonstrate that no harm will come to humans or the environment. I would like you to take a moment and tell me or think about it yourself. Can you think of a time when a chemical, a product, a process was introduced into the environment without first demonstrating that there would be no human harm? When I was a student, the pollution that was most concerning to us in New Jersey was MTBE. MTBE stands for methyl tert butyl ether, and it's a gasoline additive. It's used to oxygenate and then raise the octane number of gasoline. And they would typically use it in the wintertime and adding it to gases in New Jersey and other states in the eastern United States that had ozone problems. And it turns out it started contaminating underground aquifers, polluting people's water, and it was highly harmful to humans. No test had been done. And so something I want to tell you, something I think is very interesting and something to feel very, very patriotic about is that the Clean Water Act, the Clean Air Act, neither one of those laws makes the assumption that we're allowed to poison each other. And that is a beautiful thing. It's a special thing. And it's something that environmental chemists, we want to protect ourselves and each other because we're not entitled to poisoning each other. And so we're going to go over lots of examples in this course and try to identify, do we think the precautionary principle was followed? And if it wasn't, why not? And who do we communicate that to? Okay, so I think the main secret to doing well in environmental chemistry is balancing units. So I want to spend a whole entire slide on this. When I give homework problems and when I give exam problems, you will get full credit if you use SI units, the units of science. The SI units for length are meters, the SI units for time are seconds, and the SI units for mass are kilograms. So the derived quantities that we're going to discuss here are important combinations of fundamental quantities. And the relationships between the fundamental and derived quantities are intimately tied to the laws of physics. For example, Newton's laws relate familiar quantities that we all know, like force and energy, to the fundamental quantities. So, for example, velocity is distance divided by time. The English units would be miles per hour, right? It's something we're very familiar with. Most of us drive or take the train. And the formula for that is length divided by time, and the dimensions are meters per second. Those are the SI units. Acceleration, this would be for speeding up, trying to beat someone off the line in our car, if we're slowing down. And this is the change in velocity with time. And velocity is length per time. And the dimensions are meters per second squared. Force is mass times acceleration, F equals ma. And the dimensions for that are kilograms times meter per second squared. And those three lines mean definition. So normally we're used to seeing equal signs. Those have two lines. When you define something and it's the very definition, it has three lines. And that's the definition for newtons. Weight is mass times acceleration of gravity, and it's the force exerted by gravity on an object. So when you weigh yourself on a scale, that's what you're measuring. It's a force, it's not your mass. And weight, F equals mg, is the same as force. It's just that the acceleration is defined as g. Work is force times distance. It's a type of energy. Force times length. The dimensions are kilograms times meter squared per second squared. And that is a very definition of joule. Kinetic energy is the energy of motion. The formula is 1/2 the mass times the velocity squared, and the dimensions are the same as for work. Temperature is really interesting. It's related through the Boltzmann constant K to the mean kinetic energy of a gas molecule. So gas molecules have energy, they're always moving, much more than the molecules in a liquid or in a solid. And here, it's that definition of kinetic energy, and it equals the Boltzmann constant times temperature. So it's non-dimensional, and the units are degrees Kelvin. And pressure is the force per unit area, and the dimensions or units for that are kilogram per meter per second squared, and that is a very definition of Pascal.